This should be our last lesson in the exponential and log before our test coming up. So if you recall, this is, I believe, the third time, but we may have done it more than that, with models that our calculators will use. So I do apologize if you don't have a calculator at home, but hopefully we explain it well enough in class that you're good. So what we can do is come up with either exponential or linear or logarithmic regressions. So in this situation, we're going to 2000. So when I go to enter this into a calculator, I'm going to let this first column be 2 because that's 2 years after 2000. So 4, 5, 7, 9, and type in the data that way. So hopefully you have a rough idea what I'm talking about. I'm going to scroll down so I can see both and hide into my calculator. So if you remember, we hit the stat key and then hit enter on edit, and then we can type in our list. So 2, 4, 5, 7, 9. You might want to hit pause in the video if I'm going too fast. I'm just typing it in with my keyboard. And then from here, I believe you have to exit out of this, so hit second mode. And then when you hit that stat key again, over to calculate, and you might want to rewatch this. I know I'm probably going fast here, but somewhere in here is an exponential regression. Kind of curious if it's that. Yeah, it must be that exponential regression. I was hoping it just said it. But anyway, I'm going to hit enter. List 1, list 2. If you want to store your regression equation, you can hit alpha trace and pick a where you want to put into y equals, and that just saves you a little bit of time. You don't have to, but I'm going to hit enter on y3. So if you watched the previous video, I have a few things still saved for a different class. And then when I hit calculate, it comes up with an equation where for a being 5,157, the b value being 1.04, and they want me to round a to the nearest integer because it's a person, 5,158. And then 1.041 is the b value. To the x power, I'm actually going to write t because I like t instead of x. And then I'm going to write p for population. But if you wanted to leave it as y, because that is what the directions say, 5,158 times 1.041 to the x power. I'm just giving you my preference here. So what we can do is sketch the graph of this, which is actually why you might want to, in your calculator, go to y equals. And if I'm following the directions, though, I would change that to 5,158. And then truncate this to be 1.041. As I scroll to the right, you can't see it anymore, it's to the x power. So you might want to change your window because it's saying from year 0 to year 50. And then we have at least 5,000 people. And maybe go up to 10,000. I don't even know if that's the right answer. Maybe just count by thousands. And when I look at that graph, oh, I probably need to go higher than that. So my window, I'm going to make my y value go up to 50,000. Okay, probably too much at this point. You could get a better estimate if you hit second graph and you look at the table to see that the highest y value goes up to 39,000, give or take. So if you use your table, we know that when t is 0, I'm going to just like put a break in the graph. You might see that where we're going from 0, 5,158, and using my table over here at year 50, I already forgot what the number was. It went up to 38,757. And this is why I don't like commas, because then they get confusing on a problem like that. And if you are unaware for exponential growth, I'm going to put it in a lighter color, like this green, that it does grow exponentially, that it looks something like that. It goes infinitely in that direction. Yeah, I think that's perfect. So by what percent does your exponential model growth increase per year? The basis to that, if you remember back to an earlier unit, earlier lesson, it's based off of the formula where we had the starting amount, Q subscript 0, and then 1 plus your percentage to the t power. So I'm going to just highlight this bit right here needs to match up with that. So that 1 plus percentage needs to equal that 1.041 number. So I would subtract that over. Now remember, that's the decimal. I want the percent. What percent does it grow? So this is 0.041. So just move that decimal over twice, and the percent would equal 4.1%. And when you get really good at this, you probably don't have to show that arithmetic to see that that's the growth percentage. So if we want to algebraically, so that's using algebra, see when that equation, 5,158 times 1.041 to the t power is going to reach 20,000, well, now we can use logs to solve this. I can divide 5,158 over, and I'm going to just use the change of base formula to change it to be log base 1.041 of that giant number over there. And feel free to simplify if you want to, but your calculator will do the math for you. And maybe before doing that, I can point out on the table, since we're already here, if I scroll up to 20,000, I can see it's somewhere between 33 and 34 years. So let's hit alpha window. The fifth option there is log base. Type in 1.041 and then alpha x to make the fraction. You can also use the division sign. Yeah, 33.7 years. But they want you to go to the nearest year, so let's go ahead and make that 34 years. So as far as what exponential equations look like, at least for this previous one that we did, what exponential growth, I guess I could have shown you, because there's a tool in here. If you hit second y equals, you can actually turn on, if I hit enter on this, and turn on that scatter plot. I'm just going to show you real quick. You can actually see the dots on there. And it might have done a slightly different exponential growth. I'm going to turn that off though, because that'll mess up my calculator if I try to do something else. But the thought process is, if you were to graph this function and draw like a line of best fit that goes through this, this looks more like a log function. This one looks like a slope y equals mx plus b. Same thing with this other one, except this would be a positive correlation for y equals mx plus b, whereas this other one is a negative correlation. Hopefully you remember those lessons. Anyway, if you look at this one, it's the exponential growth. It goes up and to the right. That's the one we're looking for. But don't forget about this one, because I believe that's the next section, is we can do the natural log model for certain things. Now, the previous one might not have been obvious that it was exponential growth, but it told you to do that. Now, if you plotted this as a scatter plot, if you plot these points, it should be increasing, but at a slower rate. But we're going to do the same thing. If I hit the stat key, edit, and then type in that data, I don't think you have to clear it out because it'll just cover up the numbers. Scroll up, and you might not need to, you may need to hit pause on the video and make sure that you have the right data. And then from here, just like before, you want to hit second quit to get out of there, stat, over to calculate, but this time we want a natural log regression. If I go through all those options, I believe that would be option 9. And again, I can store that equation. I'm going to choose the third option here, so I don't have to type it in again. And so what this equation is negative 74. It says round both to the nearest integer, so I'll just leave it as negative 74 for A. And then B in my problem is 37 natural log of x. So following the directions is what they want, but it might actually make sense to some of you to rewrite it with those variables like h equals negative 74 plus 37 natural log of d for the days and the height. So the benefit to this is we can now make our scatter plot, and we could go to the graph. Now I'm going to look at the table first to see that my y values go all the way up to about 100. And if I go back to the original setting, starts at a negative number. So when I go to my window, I think I'm going to go from 0 to 100. I think I'm just going to make it negative 100 up to positive 100. I'll just count by tens. Not a big deal. But you can see the graph that looks something like that. So what I would encourage you to do is plot some points like 1, negative 74. And then over here, where it was 100, I already forgot what the number was, but it was really close to 100. Let me just jump up to 100, go to my table. There you go, about 97. But either way, the graph has that logarithmic behavior in there. And so the next question, when it reaches a height of 4, we're going to take that equation. So I kind of goofed up on this, and you can see I already jumped ahead because it's 4 feet. Missed that one because earlier the height was in inches. So make sure you pay close attention. Clearly I messed that up. Well, if you remember that 4 feet, you'd have to multiply by 12 to get into inches. There's 12 inches in a foot. So this should actually be 48. And when I add 74 over, so looking at my calculator, it's going to have the wrong answer right there. So 48 plus 74 is 122. There we go. So it's okay to get the wrong answer. You just might want to take some time and go back and see what the right answer is. And so you're left with 37 natural log of d. So in order to solve this, you divide the 37 over, and then to undo the natural log, you take e to both sides. So that's why my work, I had this answer. I just need to go back and change that 78 to be 122. So it looks about 27 days. Definitely want to fix that answer. I knew something was wrong because as I looked in the next one, if you're going to emerge from the ground, if you're unaware of some of these words, like germinate, you didn't know that, emerge from the ground, basically it's just saying, hey, when's this happening right here? Getting above the ground, and essentially same formula, but just set it equal to 0. Forgot my 7 in there. So as I add 74 over and divide by 37, to solve this, you take e to both sides. And I'm going to show you on the calculator because I'm running out of time here. $74. That would get an answer of about 7 days. And then the last question is a logarithmic has this behavior. So we're looking at option 4. You should be ready for the homework now.